let's just assume that for the moment, physicists, the whole world has forgotten what is a particle and what is a wave. So they decide to find out, and they decide to just test all the elementary things, the subatomic and the subatomic things that make up everything. So once they figure out those are waves or particles, they can figure out whether everything is a wave or particles. But they know the properties of waves and particles. So they conduct this experiment. It's called double slit. They hold a gun here against before a wall, and that wall is broken up here, and this is nanometers wide, very small. And they know that if they shoot out the things, we're not going to call them particles or waves yet, the things, the elementary things, the subatomic things, if it's a wave, it's going to pass through these slits, and it's going to spread out like that, and it's going to create an interference pattern. Okay, I'm not going to go into the details of the interference pattern. There are very good videos about it, but then basically it just creates a pattern of intensity of whatever the wave is made of. Okay, that makes at least intuitive sense to me, and I hope it does to you also. So anything that creates the interference pattern is a wave. So they find out, and this was actually carried out, that everything, electrons, protons, neutrons, blah blah blah, everything is, the neutron wasn't found out, but then every single thing was a wave. So now they are not fully ready to reconcile to the actuality of the things actually being waves. So they decided to just experiment with these waves more, but hold the notion behind that they were particles. They suddenly remember that it's all particles again. So what they do, so when you're experimenting in the wave, what you would like to know is its wave function. A wave function is nothing but a mathematical description of the wave. A function is just any other thing that can be plotted on the graph. I think that's how you view functions. And same basic thing, a wave function just gives you a plot on the graph that is in the shape of the wave. And suppose that wave changes according to time, as many wave things do, like sound waves, water waves, because they propagate, they move through space and time. So, the wave function can also be a function of time, so that if you plug in a time to it, and if you also give it a position, it will tell you actually at that time, at that position, what the heck is the wave doing. Is it high, is it low, is it disappeared, or whatever it is. Now, there's also the idea of a potential energy function, the potential energy being just plotted against time and position, but we're just going to consider potential energy plotted against position. If any of the ideas sound like nonsense to you, just ponder about them. They're practically simple. And that's all you need to know what I'm going to tell you now. This, don't run away, is the Schrodinger equation. This guy called Schrodinger is practically a genius. Wrote this, and I really admire it because I took about 5 days to learn, just get my head around this equation. Now, this equation, what it tells you, what it lets you do is it lets you solve for the wave function, which is used, as I told you before, to know about the wave particle more. So then, you might recognize this is the potential energy function. It's multiplied by the wave function, but that's just an attribute of the equation. And for different potential energies, since they influence the particle differently, that's why we are concerned about them, they give us different solutions to the Schrodinger equation. And if you notice, the mass of the particle is also here. So we are not completely getting rid of the idea that the particle is a particle, we're just also including the wave there. And you must know that at the time this was published, I think 1926 or something, people were still not very clear about what the wave was. And I'm just going to give you a basic overview of a very hazy overview of the Schrodinger equation. This entire term is called the Hamiltonian, and then it just lets you, it's just basically the kinetic energy plus potential energy. This term is the momentum squared over 2m, and that just is the kinetic energy if you manipulate the terms. Now for the best part.
Max Born postulated the meaning of the wave function to be non-dual, and he told that every single point on the wave front signifies stands for the probability that the wave or the particle will be found at that point. It gives you a really nice, amazing description of the particle. It says that the particle is in all places because of the probability of staying in all places, but it's not a place because the particle has to be in one place. But it's in all places because there's a probability. To give you a deeper understanding of what we're talking about, measure anything here. Okay, measurement is actually this is the Copenhagen interpretation. Considering we accept the probability, the interpretation of the wave function, we can say, but we know we've seen that for our eyes, with the quantum theorists have seen that when you measure anything, you can see it is actually there. It's actually the particle is taking one particular position out of its many positions. You cannot see it. It exists in a superposition of states, i.e., it exists depending on its probability in all the places probabilistically. Just let that seep into you, and right now, can you see that thing which you just measured? It's existing in a superposition in a beautiful state. You're measuring it again, it's in a normal state again.